welcome back everybody. So this is our last short lecture on 2D problems on dimensions, and in this one specifically we're looking at continuous injection. So as illustrated down here, this would be a landfill or a source of contamination with a little spill here and going downstream. And of course, when we're dealing with groundwater contamination, aquifers, we're looking at typically a 2D spread, and so those cases with continuous sources are very important, very common. So again, landfill with a leak is an example. If you have barrels of contaminants in the ground, for example, leaking, same thing, we have a continuous source that keeps leaking over time, and the question is, how do we deal with these types of problems? So here are the basic equations that we've seen. So again, this is our pulse response for a 2D problem, and we've seen this over and over. You can see here the 4 pi t at the bottom, square root of the dispersion coefficient in the x and y direction. Again, an advective flux in the downstream or in the down gradient direction. So u is the velocity, right? The aquifer velocity down gradient, and then y, of course, there's no net velocity in the cross direction, so we just have the y. So again, this equation we've seen over and over, and we call it a Green's function because, again, this is for a pulse of mass 1, right? So this is kind of the fundamental solution for a 2D problem for a pulse of mass 1. And if you remember from our previous lectures on convolutions, when we have a continuous source, we can convolve this fundamental solution for a pulse of mass 1, that Green's function, with any initial condition, essentially, that we want. So if we have a continuous source that keeps leaking continuously into the aquifer, we can basically use this modifier here instead of the 1, right, for the fundamental solution. So this is C0 Q over B dt, which is equivalent to m over z, as we've seen before, right? So again, the dt here is to eliminate the time in the discharge, right? So these are volumes per time times time, that's just a volume. Volume over b, again, is the same as z is the thickness of the aquifer. So now we have a volume divided by the thickness, that's just the area. So this is equivalent to C0a, as we've seen before, which is also equivalent to m over, well, b, I guess, in this case, call that b. Okay, thickness of the aquifer. Okay, so all of this is consistent, and now we have a fundamental solution for every little time step. Okay, so dt now would be the little time step at which, every dt we have the same amount of mass released into that aquifer. Now, if we apply the convolution integral, remember that the convolution is essentially just, summing over all the little pulses, over time. So this, assuming this is a constant, this is out of the integral, and now we can integrate, 1 over tau. So again, the tau is taken from here, right? That time that was here, we now put it inside the integral. So 1 over tau, exponential is the same as we had before. D tau, right, is taken from here. So again, if we go back, this becomes d tau, 1 over t here becomes 1 over tau, and those t's here becomes taus, and then we can just sum over them. Okay? One thing that's important to note, okay, so this integral equation in 2D is actually pretty hard to solve. You can do it with, some computer languages. In Excel, there's no real easy way to do this, but again, this is simply a sum over all the little pulses. So I'll show you in a second, how we can use, basically solve for each pulse, over time, and then just sum them up to obtain that solution. One thing of note is that there is a steady state solution. I don't know if you can hear that wind, but there's some storming going on around me here. Okay, so there is a steady state solution that's given in Fetter here. So the steady state is because, again, it's a continuous injection, right? So after some time, at least in some places, right, even though there's continuously more and more and more things coming in, there's a steady state, meaning things are not changing, right? If you go, let's say, 10 meters downstream of the leak, right, that concentration is going to be essentially the concentration inside the tank that is leaking, right? So there is a steady state 10 meters downstream, so on and so forth, right? If you go 100 meters downstream, that steady state will arrive later, right? It's going to take more time to equilibrate, but at some point there will be some equilibrium between the source contamination and the aquifer behavior. So everywhere, right, if you allow enough time, there will be some equilibrium solutions or some steady state solutions, some things that don't evolve. And these involve the Bessel function of the second kind, and I'll show you in a second how we use them, but essentially this is, the analytical solution for the steady state solution, which is really convenient because oftentimes you want to know, well, in a year from now, what is going to be the solution, at some place, and hopefully, if you allow enough time, right, that would be a steady state solution, so you can get a guess of, what that would be. Here's an example. So, statement, a waste liquid containing fluoride at a concentration of 133 milligrams per liter is pumped into a shallow disposal pit located above a thin 175 meter thick 2D aquifer at a rate of 3.66 cubic meters per day for many years. The average linear velocity of the groundwater is 0.187 meters per day. Assume that the transverse dispersion is 10% of the longitudinal dispersion, per usual. If the disposal pit is assumed to be at a location 0 and 0, what would be the concentration of fluoride in a monitoring well 123 meters downstream and 60 meters to the side? Assume that the fluoride is non-reactive and non-adsorbed by the aquifer, meaning it's a conservative, so it behaves, like a conservative tracer. We'll do reactive tracer in the next module. Okay, so we apply our usual equations again. So find the longitudinal dispersivity is almost 5 meters. Then the transverse dispersion is a tenth of, the longitudinal dispersion is 0.9 square meters per day. The transverse is 10% of that. And then essentially you just plug in those numbers into your analytical solution. So you assume that this is, enough time that things are at equilibrium because things have been going on for a long time. Okay, so now if we plug everything in, right, we find that the steady state concentration at 123 meters downstream and 16 meters to the side. Everything else we know C0, we know Q, we know B, we know the two dispersion coefficients that we just calculated, we know the downstream velocity that was given to us. So everything is known essentially at this point. So one thing that you may not know is how to use that Bessel function. Again, it's just a function like an exponential or, a log or something like this. So in Excel, for example, there is a, Bessel K, which is that Bessel function of the second kind. And again, once you crunch all the numbers, when you plug in all the numbers, right, you get K0 of 13.52, and this is what I'm calculating here, K0 of 13.52, and this is the way you do it in Excel. Okay, so in Excel you can just go ahead, plug those in, and find the result, as 19.2 milligrams per liter. Okay, and then that's the concentration, the steady state concentration in the well that is located 123 meters downstream and 16 meters to the side of the leak. Okay. Now, finally, I'm just going to show you. So this is done in Matlab because, again, in Excel, it's not very convenient or very easy to do it. But you can see now how you have here that constant source, obviously, and then over time. And again, understand that the steady state solution, right? You can almost see it. Well, that would be the concentration in a well somewhere. But let me. Oops, excuse me. Okay. What I want to highlight here is, let's say, for example, that you have a well right here, right? You can understand that over time, like as of now in the simulation, things are not changing, right? So if we are looking at the concentration in that well, over time, at the beginning, it's at 0. So C versus time. Excuse me, this is on top of me here. So if we look at C versus time, this is what you have on the left. It starts at 0, and then the front hits with some dispersion. Right, and then we end up with that error function solution that we've seen in those early lectures in contamination, right? So you have that rise to some plateau, and then you get to a plateau, which is your steady state here for that point. Right? So there is a steady state at any point in the domain, essentially, right? That you can identify with, using Fedor's, that Bessel function thing. Here's the Matlab code I use for this, just to show you here that this PDF here is your Green's function. So 1, right, so I replace this with 1 here. 1 divided by 4 pi t square root of dd, 4 pi t squared of dd, exponential minus, let me clean up a bit here, exponential minus, x minus ut, and so init x here is just the location of the initial of the spill, right? So if it's at 0 and 0, then those don't matter. If it's somewhere else, then you can just put that in. Again, u is your velocity, and then for the y, you don't have any velocity. You know, 4 dt, 4 dt, 4 dt here, the x and the y, and then all your unknowns. Okay, so this is just how you write this equation in Matlab, essentially. And then you just multiply this by C0 over Q over B, and then there's a dt that comes in also. Okay, so it's just on a loop, right? And then you just sum over, you know, you do the convolution by hand, basically. You're just solving that pulse over and over and over, you know, through a loop that is essentially all the times that you have. Okay, and this is how you model, again, a continuous spill into an aquifer in 2 dimensions. All right, I think this is it for now. In the next lecture, we're switching topics a little bit, so we'll get into reactive transport and really start looking at reactions and how things, you know, how transport of contaminants, you know, can have, you know, some contaminants can absorb, they can lose mass, etc. So we'll delve into the reactive transport. Thank you.